Good morning, everyone. Welcome to our lecture. Can you confirm that you can hear me? Okay, thank you, Muteb. We are still continuing with 6.3, 6.2, a bit of 6.2, and then we get into 6.3. So we are continuing to look at complex numbers, and we introduced the notion of a modulus of a function, of a complex number, and then we are going to discuss a bit more about that. So if you are given a complex number z, which is equal to a plus bi, then we know that the modulus of z is going to be that, right? So to look at it from a geometrical point of view, we can say if you are given two complex numbers z and w, then the modulus of z minus w is actually just the distance between z and w. So if you think of that z and w that are given in that complex plane, then what we are talking about is the distance between these two. That's what the modulus is about. And if you want the modulus of, if you find this modulus of z minus y, again, it's the same thing. We are talking about the distance between the two complex numbers. And then when we say the modulus of z is equal to a, what we are saying is the distance from the complex number 0 there up until there is what we are calling, what we are saying is equal to a, right? So in other words, what we are saying is the modulus of z minus 0 plus 0i is equal to a. That's what we mean when we say this. Right. This should help us to look at, I had done one example yesterday, but we'll look at a couple of more examples to see how we can sketch some regions that are restricted in terms of complex numbers in the Gantt diagram. Right, so let's see. So we've got this question which says, well, we're supposed to sketch this or draw this, and we want to see how we can do that. We can find this region. Right, so what we have is, this modulus of z minus 3 plus 2i, right, can be rewritten as z minus 3 minus 2i, like that. And then we can think of this complex number as our w in this example here, right? Where we were saying the modulus from z minus, the modulus of z minus w is the distance between z and w. So what we are saying is the modulus of z minus this is the distance between z and this complex number w. We are saying it's less than 2. So here we want to find all the points, so all the complex numbers such that this is satisfied. So first of all, we have to think about z minus 3 minus 2i being equal to 2, and then we can then look at what the inequality implies after we've found what this means, right? So if you've got your complex plane there, and you've got 1, 2, 3 there, and then you've got minus 1, minus 2. Then we want to find what this point is, and the point is going to be 3 minus 2i, right? So if I say 1, 2, 3, so 1, 2, 1, 2 there, then it will be 3 minus 2i, it will be somewhere there. And then we are told we want all the points such that the distance between that point and this point is going to be equal to 2, right? So we will draw like a sketch there. So it will be a circle. So those will be the points there. So if you think about what this will be, it will be equal to 2, like what is given in the question, right? So now what we want to is, so now we've got a circle, and here I've drawn it in bold. Technically, when you're doing it for the first time, you should do it as a dotted circle, because if the inequality here doesn't have the option of equal to, then you are not going to be including the boundary of that circle, right? You're not going to include the circle itself, but because in this case equal sign is part of the properties, then we know we are going to include the circle itself. So from here, then we then say here now we want all the points. So basically, if you look at this, what we are saying is we want all the points z such that the distance between that point and this point, which I call w, is at most 2. That's what we are saying. So for it to be at most 2, it has to be inside the circle, right? So this becomes the region that we are talking about. So the interior of the circle and the boundary itself will be included. So that will be the sketch of this object over there. Right. Now let's look at a different type of question. And this one says that we want to sketch the set of all points such that the real part of z squared is equal to 4, right? So we want all the points that satisfy this. So for us to be able to do that, we say let z be equal to x plus iy, where x, y are real numbers, right? And then from here, for us to find the real part of z squared, we have to find what is z squared first. So we say z squared is going to be equal to z times z, which is equal to x plus iy times x plus iy, right? Or yi. Maybe I should use what we have been using all along. So that's yi there. And then if we do the calculation, we'll see that we will get x squared minus y squared plus 2xy. And this is, remember, this is the standard form. Right. So what we are told is the real part of z squared is equal to 4. And in this case, our real part is x squared minus y squared. So the real part of z squared is x squared minus y squared, as we have seen. And we are saying that is equal to 4. Right. And then, so in other words, we want all the complex numbers z which are equal to x plus yi such that x squared minus y squared is equal to 4, right? So now we want to figure out what this is. So if you go back to chapter 5, you will realize that this is something that is familiar. So I'm going to rewrite it. So this can be written as x minus 0 squared over 2 squared. If we divide by 4 throughout, right, we end up with something like this. Sorry, x minus 0 again over 2 squared is equal to 1, right? And if you remember your chapter 5, you remember that this is just a hyperbola, right? So if we draw our arcant plane there, so we've got the imaginary axis, the real axis, and we can see that our asymptotes x is equal to y and x is equal to minus y, right? But in terms of the, so this would be what would happen if you are dealing with R2, but in this case we are in the complex plane, so we would say the real part of z, which is x, is going to be equal to the imaginary part of z. So this is that equation. And then with this one, we are saying the real part of z is equal to the minus the imaginary part of z, right? And so this is going to be this equation. So real part of z equal to minus imaginary part of z. So that is that line. And then this line is going to be real part of z equal to imaginary part of z, right? So those are the two lines that we have there. And then because of these twos, we know that we are going to have minus 2 there and a 2 there, and our hyperbola will look like this. Something like that. The sketch is not nice, but I think it gets the message across, and so we get those like that. So this becomes our this becomes the region that we want, right? So these two curves become the region that we want, that satisfy what we are given there. And that's how you get this. So you can get all these different things by using prior knowledge that you already have. So don't forget that you can be asked things that you have done in previous chapters in other chapters, right? You just need to apply that knowledge to be able to figure out what's happening. So that is the solution to that one. If you have any questions, please feel free to post in the chat. Otherwise, we are going to section 6.4, and we are going to look at the polar form and De Moivre's theorem. And the motivation behind polar form, which we haven't defined, but we are going to define as we go, is this question, or at least this type of question. Can you find 1 plus 2i to the 2023 quickly, right? So you've got a complex number there, and then you want to find its powers. So quickly might not really be the word, but efficiently, or at least sort of cutting corners, not doing the direct, because if you are going to do the direct, you want to multiply 1 plus 2i 223 times. That is not going to be a pretty sight. So we want to develop efficient algorithms to be able to sort of do this quite quickly, right? So that's part of the motivation of now moving to polar form. So we've got the standard form, which is what we have here. But if we change this complex number to polar form, you'll see that this question might becomes easier to look at. So we are going to develop the theory to be able to sort of answer this type of a question, to say yes, we can find it quickly if we only change the form that we are using. Right, so we'll start off with a theorem. This is theorem 6.3.1 in the textbook. And it says, if P and Q are real numbers and P squared plus Q squared is equal to 1, then there exists a unique real number theta, which is between minus pi and pi, such that P is equal to sine theta, and then Q is going to be equal to cos theta. And so what are we saying? We're saying we've got two real numbers such that P squared plus Q squared is equal to 1. And then we are saying we will always find a theta, so an angle such that this happens. Right. And the proof is in the textbook, so you can go and look at the proof, but I'll just illustrate using a sketch what it's sort of saying. So if you think about it, if you think about P and Q, any P and Q that satisfy this equation is going to lie on the circle, on the unit circle, right? So circle whose radius is 1 and its center is the origin. That's really what it's saying. So any point P, any combination of P and Q should satisfy this, should be on the line, on the circle, right, on this unit circle. So if I, for example, take my my P and Q to be such that this is the point, then what the theorem is saying is, so if I take my P and Q like that, then let me draw a triangle here. So if you think about this, this would be equal to Q, the length of this, and then the length of that is P, and then the length of this is 1, right? And then we've got a theta here. So if you think about theta, you will see that if I say cos theta, I am going to have, for me to get cos theta, I'm going to say this is going to be opposite of hypotenuse, which is Q over 1. And then if I want to find sine theta, I will say adjacent, which is P over hypotenuse, which is that. And then we end up with Q being equal to cos theta. And then we also end up with P being equal to sine theta, right? So we can see that we get this theta, and this theta is unique because if you move to another point, you're going to get another theta and so forth. So that's sort of the idea here behind this. I hope that sort of illustrates what's happening here. Right. We need this theorem to be able to prove this statement, and then we will define the polar form of a complex number. And this is theorem 6.3.2. So it says, let Z be equal to A plus BI, which is a non-zero complex number, right? Then there exists a unique real number, theta, which is between minus pi and pi. So one thing that I didn't mention, so you see that theta is between minus pi and pi. So that covers like all the angles that you can get in in a revolution, right? So and then it's unique, so we need that for this theorem. We want it to be unique, and between those angles there, and then it says, so this happens such that the real part of z, so the real part of this is going to be r cos theta, and then the imaginary part is going to be r sine theta, right? And then r is going to be the modulus of z. So that's what we have there. That's what the theorem is saying. If you're given any complex number, any non-zero complex number, you can write it in this form. And so we are going to look at the proof of this one. So if we say r is the modulus of z, we know that that is going to be equal to the square root of a squared plus b squared. And here remember that our z is not equal to 0, so it's non-zero. So what we are saying is r, which is the modulus of z, is not going to be equal to 0, because if it's not equal to 0, then the square root here is not going to be equal to 0, right? And r is a real number, right? Now, from here we can then say z over r is going to be equal to a over r. So maybe let me start by saying, remember that z is equal to a plus bi, and then if I divide throughout by r, I've got this over r, I've got this over r, which can be written as a over r plus b over r I, right? And then if I say z over r squared, it is going to be equal to not z over r squared, but the modulus of z over r squared is going to be equal to the real part squared plus the imaginary part squared. If you remember our theorem that told us that if you've got the modulus squared is going to be that times that times its conjugate, which gives you sort of a squared plus b squared, right? So we get this scenario because in this case our complex number is z over r, and if you calculate this, you'll see that this is just a squared plus b squared, and then if you look at the bottom, so the top part will be a squared plus b squared. If you look at the bottom, if you square r, you are going to get a squared over b squared, a squared plus b squared, which is going to be equal to 1, like that. And once you see that it's equal to 1, we know that by theorem 6.3.1 that there is going to exist. So there exists a unique real number theta, which is between minus pi and pi, such that a over r, because here what we said was a over r plus that is going to be equal to 1. So once that happens, we are in the scenario of 6.3.1. We just take whatever is here, whatever is there. We know that a over r is going to be equal to cos theta, and then b over r is going to be equal to sine theta. And then this means that the real part of z, which is equal to a, is going to be equal to, so a here is going to be equal, if you multiply r by r both sides, you get r cos theta, and for the imaginary part, you're going to have b, if you multiply r both sides, you get, this is b, which is equal to r sine theta, and this is what we wanted. So we have proved the theorem, and that is it. Right, so now because we've got this nice theorem that tells us that for any non-zero complex number, we can find this theta such that this happens. Now we can define the polar form of a complex number. So it says, let Z be a complex number. Then a polar form of Z is going to be equal to R. Z is equal to R cos theta plus I sine theta if Z is a non-zero complex number, and if it's a zero if it's equal to 0, then it will look like that. The modulus is 0, and then whatever is inside would be 0. So that's what happens when you have that, right? So where R is the modulus of Z and theta is a real number, right? Such that the real part of Z is R cos theta and the imaginary part is R sine theta. So that's how we define the a polar form of Z. There's another one that we'll talk, I think, on Friday, but this is the first one. A polar form of Z would look like that, right? So what we need to note is, in this case, if theta works, right? So here it doesn't really specify the range of theta. In the definition here, you can see that theta can be anything. And we know from previous theory, I think in 114, that if theta is going to be, we know that basically that cos theta is equal to cos theta plus 2 pi k for some integer k, right? So in other words, if theta works, theta plus 2 pi k, where k is an integer, is also going to work in this scenario here, right? And so in essence, you can get an infinite number of thetas that you can get, right? However, we've got what we call the principal argument. So an argument is just this theta that is going to work in this scenario, right? So the argument of Z is just theta. Theta is, it's not specified what it is. And then R is going to be the modulus of Z. We know that. And then from here, we have what is called principal argument. So this is not just an argument, but principal argument. And that is the angle that is between that one that we said is unique between this interval. That is what we call the principal argument. So that is what we are going to be required to use pretty much in any situation. So if you find that you don't have that, then it's going to be, you will have to, whatever angle you get or whatever argument you get, you have to find the principal argument. And we'll see in a minute how we can do that. Right. So just as examples to see what the arguments. So if you think of the argument of -2, the complex number -2, then you are going to say, well, if that's the case, I've got the real part there, the imaginary part there. If I think of theta, theta is going to be there. And that will be the angle from 0 to there. So here, if you think about this, this is when theta is equal to 0. And if you are here, if you're thinking about that, then theta is equal to pi over 2. If you're thinking about this one, theta is equal to minus pi over 2. So remember, when we want angles that are here, this is not going to be 3 pi over 2, but minus pi over 2, right? And then this would be equal to theta is equal to pi, right? This side. Right, so that will be our diagram there. So if you want to find the argument of -2, -2 will be somewhere here. So if you look at the angle there, theta, it's going to be equal to pi. And if you think about the argument of 4, for example, 4 will be on this line. So somewhere there will be a 4, and the argument will be theta is equal to 0. So the argument in this case would be equal to 0. Right, we'll do a bit more examples as we go. And then one thing you need to note is if your angle is not in between these ones, so you find some angle that is bigger or smaller than minus pi or pi minus pi, then to fix it, to find the principal argument, all you need is to say if it's too big, you have to subtract 2 pi. And if you find out that it's still too big, you subtract 2 pi you subtract 2 pi again. And if it's too small, then you add 2 pi. So for example, if you've got let me just say you've got minus 3 pi, so this is too small, so you have to add 2 pi, and then you get minus pi, right? So this would be this is not even in there yet because minus pi is not in the interval, so you have to add 2 pi again to this one, and you are going to get that to be equal to pi, and now pi is in the interval there. So then you get an angle which is in which is pretty much the principal argument would then be pi. You started off, maybe you got minus 3 pi, 3 pi, so you then have to find the principal argument which will be pi. And if you've got say 5 pi over 2, then this is too big, then you have to subtract 2 pi, and then you'll see that this will just be pi over 2, and pi over 2 is within our interval, so therefore you would have found the principal argument. Let's look at an example to see this in motion or in practice. So the example says express this angle, this complex number minus 3 plus minus the square root of 3 plus I in polar form and using principal argument. So whatever arguments we get, we want the unique one, the principal argument. And then we want to also then sketch this in an Gantt plane. So let's look at that. So first thing is, so what we are trying to use is this definition. So we know that the modulus of, so R being the modulus of Z is going to be equal to the square root of minus the square root of 3 squared plus 1 squared, which is going to be equal to the square root of, so if you square that, we get 3 plus 1, which is 4, and it's going to be equal to 2, right? So that is the modulus of R. And then once we find that, then we are going to say Z, which is equal to minus the square root of 3 plus I, is going to be equal to 2, because we know R is 2. We have found 2. We are going to then say this is 2 cos theta plus I sine theta, right? That's what the definition says here. And then from here, this would mean that if I take the real part of Z, on the left hand side, I know this is going to be the square root of minus the square root of 3. And then if I take the left hand side, I've got 2 cos theta. And I can call this equation 1. And then if I take the imaginary part of Z, on on the left hand side, the imaginary part is going to be equal to 1, and then the real part is going to be equal to, sorry, the imaginary part on the right hand side is going to be equal to 2 sine theta. And this is going to help me figure out what is going to be my principal argument. So from 1, what it means is cos theta is going to be equal to the square root of minus the square root of 3 over 2. And from there, we then see that the only possible arguments we are going to get is 5 pi over 6 or minus 5 pi over 6. Right. And so we've got two angles or two arguments that we have, but we still need to figure out which one is the right one. And if we draw this little quadrant here, we know that these are always positive. Well, all the sine, cos, and tan are positive in the first quadrant. In the second quadrant, sine is the only one that is positive. In the third quadrant, tan is the only one, and then in the fourth quadrant, cos is the only one. So we can sort of use this to figure out what's happening. So now we've got. So if we look at this, we can see that cos is negative. What do I want to say here? Okay. Anyway, we see that cos theta is going to be either minus 5 pi over 6 or minus 5 pi over 6, because it's going to be either here or there, right? Because it's negative, right? So either in there or in there. And then from here, we still need to figure out which one is the right one. So if we use the second one tells us that sine theta is equal to half, which tells that that sine is actually positive. So this one can be excluded. So we are left with this one. And this one is 5 pi over 6. So in other words, theta is going to be 5 pi over 6. And that is our principal argument. Right, so just to recap, we saw that cos theta, so you can find what is the cos inverse of this. So you are going to have two possibilities, either that or that. Why? Because cos is only positive in here and in there. So it's negative in the second quadrant and third quadrant. So that's why we've got these two options here. And then we then use the second equation there to figure out, and we see that sine is actually positive. So therefore, this would have been negative. If it was in here, it would have been negative, which would have then not satisfied the second equation. So it means it should be in the second quadrant, which is 5 pi over 6. So that's how we figure out that. And so now we know that z can be written as 2 cos 5 pi over 6 plus I sine 5 pi over 6. And from here, we can then sketch the complex number in the complex plane. So let's now sketch what it looks like. So you've got your real axis, imaginary axis, and then this is going to be in the second quadrant, right? So we see that that's just 5 pi over 6, and then you've got so the point here, I'm just assuming this is 2, so the modulus of z is 2 there. So this point is going to be our complex number, and that is it. So that will be the sketch of that. Right. Okay, so you can go and look at more questions on this. And now we get into a nice theorem that tells us what happens if we are to multiply two complex numbers. And I'm not sure if I'll have enough time to prove it. I'm sure it will be fine. And then we'll stop there. Right, so the theorem is theorem 6.36. So if you have got two complex numbers, if Z and W are complex numbers, so you've got two complex numbers in polar form. So the polar form that we have just talked about, where Z is going to be equal to R1 cos theta 1 plus I sine theta 1, and W is going to be equal to R2 times cos theta 2 plus I sine theta 2. Then multiplying them is not that difficult. Z times W is going to be equal to R1 times R2, so just the product of the moduli of these two complex numbers, times cos theta 1 plus theta 2. So we just need to add the angles or the arguments that we have, time plus I sine theta 1 plus theta 2. So that's what we get. So that's how we multiply them in polar form, two complex numbers, and this will come in handy as we go on. We still want to answer our question, can we multiply a complex number to the power something, some big number, quickly, right? And this is part of the easing of the problem. So if we can multiply two complex numbers, this is all we need, right? Okay, let's look at the proof of the theorem. So let's look at the left-hand side that we have. So if we start off with ZW, we are going to have R1 cos theta 1, right, plus I sine theta 1, like that, right? That's the Z, and then our W is going to be R2 cos theta 2 plus I sine theta 2, like that, right? And then if we multiply the two, we can then say, well, we can take these ones out. So we've got R1 times R2, and then what is left is to multiply this by that. So we get cos theta 1 cos theta 2 plus I sine theta 1 plus cos theta 2 plus cos theta 1 plus we want to multiply here, not add, sine theta 2, I'm just going to put the I, maybe let me just put it there, and then plus I squared sine theta 1 times sine theta 2. So that's what we get if we do that expansion. And we can then say, let's take the real part and the imaginary part. So we get R1, R2 times cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. So here we just made this equal, I squared is equal to minus 1, so that works. So that's the real part. And then the imaginary part is going to be I times sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. And that's what we have, right? But we know something about, we've got some double angle identities that we know, and we know that cos theta 1, cos theta 2 minus sine theta 1, sine theta 2 is going to be equal to cos theta 1 plus theta 2. And we also know that sine theta 1 cos theta 2 plus cos theta 1 sine theta 2 is equal to sine theta 1 plus theta 2. And so therefore, from here, we can replace those in our equation here, or in our expression there. So this gives us that ZW is going to be equal to R1, R2, and then if we replace that with that, we get that is going to be cos theta 1 plus cos theta 2, and then plus I sine theta 1 plus theta 2, and that is what we wanted, right? Because that's what the statement said. So this makes our life much more easier to multiply complex numbers. Well, it should in the long run, and we'll see this play out. I don't know if I've got enough time to do an example just to see what happens. Maybe let me start it off and then we'll see how much we can do. So let's look at an example. So let W be equal to 1 plus I and Z be equal to I. And what we want is to find ZW. So we want to write it in polar form. So this one is a simple one. If you're multiplying using what you already know, which is just multiplying, it will be easy. But I'm just trying to illustrate how you would go about multiplying two complex numbers, right? So the first thing is to deal with this one. So if you find the modulus of W, you will see that it is going to be equal to 2, and theta is going to be equal to pi over 4. So if you find the pi there, you will see it's in the first quadrant, and if you find so tan theta will be equal to 1 over 1, so therefore theta is going to be pi over 4, right? And so therefore what it means is W can be written as the square root of 2 times cos pi over 4 plus I sine pi over 4, right? And if we are to write, if we are to write I in terms of in polar form, then we've got I, the modulus of I is going to be equal to 1. And if you look at the argument of I, is going to be equal to pi over 2. If you just draw it, you'll see that that is the case. So I will be somewhere here, and so if you think about the modulus, it's 1, and then the argument is just what we have there, which is pi over 2. So in other words, I can be written as 1 times cos pi over 2 plus I sine pi over 2, like that. Maybe let me put brackets there. And then if you are to multiply the 2, then you say by theorem 6.3.6 z times w is going to be equal to the square root of 2 cos pi over 4 plus I sine pi over 4, like that. And then from here we know that times 1 times cos pi over 2 plus I sine pi over 2. And from there we then see that this is just the square root of 2 times 1, right? And then on the angles we just add. So pi over 4 plus pi over 2 plus I sine pi over 4 plus pi over 2, like that, right? And this becomes the square root of 2 cos, if you add the two angles there, you get 3 pi over 4 plus I sine 3 pi over 4, and that is it. So that's how we would do it. This was a simple one, but if you get a complicated one, you see what happens. So that is that. I think I will stop here. If you have any questions, I am here for a minute or so. Otherwise, enjoy the rest of your day. Thank you. Okay, it seems that there are no questions, so thank you for your attention. Enjoy the rest of your day. See you on Friday. Bye.